Welcome to the first problem of the conservation of energy, and this will be a standard, fairly standard conservation of energy problem. And I'm going to show you how to use this new equation that we just found out in the last video. So let's go ahead and get started. I start with a problem out of the book, and it says a child and a sled with a combined mass of 50 kilograms slide down a frictionless hill that is 7.34 meters high. If the sled starts from rest, what is its speed at the bottom of the hill? Well, in this problem, they actually give us too much information, or information that we don't need. And I'll show you that a little bit later. But right now, I want to go ahead and start by highlighting all of my information that I want to know. So, a child in a sled with a combined mass of 50 kilograms slides down a frictionless hill that is 7.34 meters high. If the sled, and I'm going to highlight this in a different color, if the sled starts from rest, so here's the sled, it starts from rest. Now that has important implications into what I want to accomplish with this problem, and it's going to help me cancel out some things. So if I look at my equation here, there's some things that I need to go ahead and mark off right off the bat. Well, if I think about my problem, I don't have any springs, so I'm going to go ahead and cancel out these spring portions of this equation because I don't need them. The spring constant is 0, and so they just go away. But there's also a couple other things that I can go ahead and start marking off. I know that it starts from rest, and that means that my initial velocity, or VI, equals 0 meters per second. And so if VI equals 0, well then this term right here is 0, and anything multiplied by 0 goes away. I also know that, or I want to note that I want to find out the speed at the bottom of the hill. So I'm choosing to look at the speed of the sled at the bottom of the hill. So the bottom of the hill we're going to go ahead and label as 0 meters, and the hill itself, from top to bottom, is 7.34 meters high. Okay, so its final height, or the final height of my sled, is actually going to be 0. So that is 0, and so the whole thing goes away. Now there's another thing that I can cancel out, and I can't stress enough how easy this is to do if you can first realize that there is no spring in the problem. If there is no spring, so 1/2 kxi squared or 1/2 kx final squared, if there's no spring in my problem, I can actually cancel out the mass because this term has mass, this term has mass, this one has mass, and this one has mass. And so all the terms have mass in them. And so if I were to divide one side by mass and divide both sides by mass, then they cancel out. So I'm left with the equation for this as being the acceleration of gravity times my initial height equals 1/2 my final velocity squared. Now, you can see how much I have simplified this whole big equation down into just these few terms. And now I want to solve for the speed at the bottom of the hill. And so I'm going to divide both sides by 1/2. All right, and those halves will cancel. And then I want to take the square root of both sides. So I'm left with, after this, the square root of g times my initial height divided by 1/2 equals my final velocity. Now it's just a matter of plugging in my numbers and working the math. So if I do that, I get the square root of 9.81 times my height, 7.34, divided by 1/2. And let's go ahead and pull up a calculator. Here's my calculator. Now the calculator for Windows is a little bit different than my normal calculator, and I have to follow a certain pattern on how I enter stuff in. So I'm going to start with inside my square root. So I have 9.81 times 7.34 and divide it by 1/2, which is 0.5. And so that's what I get inside of my radical, and then I take the square root. And the square root is right up here. For some reason they put the cube root down here and then the y root up here, but then the square root over here on this calculator is right there. And if I click it, then I get roughly 12. All right, so my answer, so my V final, is going to equal 12 meters per second. And that's my answer. All right. Now, I really want you to look at how you can cancel out a lot of the terms in this long equation. Especially look at how you can cancel out the mass. As soon as springs are not involved, get rid of the masses. You don't need them. They go away. And that has to do with the fact that gravity affects or causes all objects to accelerate at the same rate no matter how much they weigh or what their mass is.